You know, it's kind of wild when you think about it. Some of the most powerful technologies we use every single day, the ones that find the fastest route, connect you with friends, and even run the entire internet, are all built on a surprisingly simple idea. It's like a hidden network of connections, and today we're going to pull back the curtain and map it out.
Seriously, just take a second. Your friends on social media, the route Google Maps finds for your road trip, the very fabric of the web itself. On the surface, they seem like totally different things, right? But underneath it all, they share this common hidden blueprint. So what is it?
So, you might think the answer is some mind-bendingly complex algorithm, but it's not. It's actually a beautifully elegant and simple way of organizing information that's all about one thing: relationships. It's called a graph. And no, we're not talking about the kind with an x and y axis from math class. In the world of computer science, a graph is just a bunch of points and the lines that connect them. That's really it. It's just a map of connections.
All right, so the best way to really get this is to just build a graph together, from the ground up. And you'll see pretty quickly that it's made of just two basic parts.
So first up, we have our vertices. You'll also hear people call them nodes. They mean the exact same thing. Just think of them as the individual items in our network. So here, we'll put down 4 of them: A, B, C, and D. Each one could stand for anything, really. A person, a city on a map, a website, you name it.
Okay, so we've got our points, now we need to connect them. And that's where edges come in. These are just the lines that show the relationship between our vertices. Let's draw some in. We'll connect A to B and A to C. Then we'll link B over to D, and finally, C connects to D too. Each line tells a story. It could be a friendship, a road, a hyperlink, whatever the connection is.
And that's it. We've just made a graph. I know it looks simple, but this basic structure right here is the absolute key to understanding massive, super complex networks.
So that leads to the next big question. This drawing is great for us humans, we can see it, but a computer doesn't have eyes. So how in the world does a machine actually remember this web of connections in its memory?
And figuring this out is a huge deal. For a computer to do anything useful with this graph, like finding the shortest path for your GPS, it can't just look at the drawing. It needs a way to translate these points and lines into the ones and zeros that it actually understands.
Well, it turns out there are 2 main ways programmers handle this. And like a lot of things in computer science, it all comes down to a classic trade-off. In this case, a battle between speed and memory.
Okay, method number 1 is called an adjacency matrix. The easiest way to think about it is like a spreadsheet or a grid. We list all our vertices, A, B, C, and D, down the side as rows, and also across the top as columns. Then we just fill it in. If there's a line between 2 vertices, say A and B, we just put a 1 where they intersect. If there's no connection, we put a 0. That's all there is to it.
So the big win here is speed. A computer can check if 2 things are connected instantly. It just has to look at one single spot in the grid to find a 1 or 0. But, and this is a huge but, the memory cost is insane. Imagine this grid for something like Facebook. You'd need a row and a column for every single user. That's billions of rows and billions of columns. You get a matrix so gigantic you couldn't possibly store it, especially since most of it would be filled with zeros.
So what's the alternative? Well, it's called an adjacency list, and it's a much more direct approach. We just forget the giant grid entirely. Instead, each vertex, each point, just keeps its own little list of who it's directly connected to. So for our vertex A, its list just has 2 things in it, B and C. For vertex B, its list has A and D. We only write down the connections that actually exist.
And right there, you see the flip side of the coin. Because we're only storing the real connections, this method is incredibly efficient with memory. It's absolutely perfect for what we call sparse graphs, networks like social media, with tons of nodes, but where each node is only connected to a handful of others. The catch? Well, it's a tiny bit slower. To check if A and D are connected, the computer has to look at A's list and see if D is on it. A little slower, yeah, but it saves a ridiculous amount of space.
All right, so matrix versus list. The showdown. Which one is actually better? Let's put them side by side and see how it all shakes out.
This really lays it all out. Look at the space row. For the matrix, the memory you need just explodes as you add more points. For the list, though, it only grows based on the actual connections you have. Now look at edge lookup. The matrix is instant. The list takes a little bit longer. So it all comes down to the bottom line. The matrix is really only good for dense graphs, networks where almost everything is connected to everything else. For sparse graphs, which is what most real-world networks are, the adjacency list is the clear champion.
Okay, enough of the theory. That was the how. Now for the fun part, the why. Let's talk about how this simple idea of points and lines is secretly powering the technology you use every single day.
And that is not an exaggeration. Once you get what a graph is, it's like you've been given a new pair of glasses to see the world. You start to see these hidden networks absolutely everywhere. Think about it. Social networks, your vertices, and your friendships are the edges. Your GPS. Cities are vertices, and the roads are edges. They're what computer networks use to route data around the globe. They're how Google originally understood the entire internet by seeing web pages as vertices and links as edges. And they're even used to map out every single airline flight path in the world.
So the next time you use a map or connect with a friend online, you'll know. You'll see that simple, elegant structure working behind the scenes. And it really makes you wonder, doesn't it? Now that we have this powerful way of seeing the world in terms of connections, what's the next huge problem we're going to solve?